Let's start lecture 2, talking about the driving forces for mass transport. For mass transport, actually, the first thing come up from your mind is probably is atomic flux, which can use to describe or quantitatively describe the mass transport. And as you learn from the fixed first law, we know atomic flux equals to minus diffusivity times the concentration gradient. And also you know that the atomic flux equals to concentration of diffusing atoms times the mobility of diffusing atoms and the driving force. And actually, this relationship we are going to show you in following slide. But here in these lectures, we are going to introduce several driving forces can drive the atomic flux. So as you learned from a previous lecture, if we have one or more driving forces coexist in your systems, definitely every driving force will contribute some on the atomic flux. So we need to modify the atomic flux here. So the driving force here in these lectures we are going to introduce to you will be included the electron migration, which means the electrical field serving as a driving force, temperature gradient, capillarity means the curvature effect, and also the stress gradient. This included the chemical potential gradient can be drive the atomic flux. So this is the outline included 5 parts. The first one we are going to describe the diffusion phenomenon. And I believe most of you will know about the driving force for diffusion is the chemical potential gradient, which means the atoms at some specific location with a higher chemical potential. Then in this case, this atom is going to move toward to the location with lower chemical potential one to decrease the total free energy of the system. So some people have some misunderstanding or think that concentration gradient probably would be is the driving force to drive the diffusion phenomenon. But as I mentioned in previous lectures, spin nodal decomposition is a very typical case to demonstrate that instead of concentration gradient, chemical potential gradient is a real exactly driving force to drive the diffusion phenomena, because in the spin nodal decomposition, atoms moves from the low concentration site toward to high concentration site. So in this case, we know that the driving force for diffusion in solid materials is a chemical potential gradient. And this is a quick review. You need to know the chemical potential of the specific atoms is related with its composition exists in these materials. And the second driving force we are going to show you is we call the electron migration. Based on this term, you know the electrons flow drive this atomic migration. So in order to have electrons flow, so in this case we know that's definitely we apply the electrical field, or you can say that there's exist of the electrical potential gradient. So this gradient will drive the electrons flow, which will make or which will cause the atomic migration. So some people probably will, this is a new idea, right? Electrons flow to drive or to push the atom's atomic flux or atomic movement. So in the beginning, this phenomenon actually was found in semiconductor industry, especially on the conducting line. In your mind, I will ask you if you have a positive ion for example, like sorry, I should use the pen. Okay, if you have a positive ion, probably some metal or something, when you apply the electrical field, this ion usually will move to cathode side, right? But however, in the experiment, the scientists found that these ions move toward to the anode under the high current density. So this implies that this observation demonstrates that the reason to drive or push these ions toward to anode is due to, after serious investigation, they find this is due to because only are observed under the high current density. So actually the real reason actually is these atoms be pushed by the electrons flow. Okay, so electrons flow can be considered as like the electron wind. Some people call it as an electron wind to bombardment this on this ion, positive ion, and push these ions move. So why this is so important to be mentioned in these lectures? Because when this positive ion, for example, like the metal ion, be pushed toward to this anode, and it will left a vacancy here, right? And as long as we have many metal ions be pushed toward to this toward to anode, and there will be lots of vacancy. As long as vacancies accumulate, then they will form a void, and the void will, as long as it gets larger and larger, then that will cause what? If this happens on the conducting line, then you will find that this will open circuit happen. It will be open circuit happen on this conducting line. So the reliability of this device would decrease dramatically, right? So this is actually electron migration is a this is why electron migration is so important. We need to know how to avoid this when we design the conducting line, right? Okay, and as you know, in the semiconductor industry, the line width actually decrease dramatically. That will result the current density increase dramatically, right? So electron migration will happen always and easily under this situation, under the high current density. So this phenomenon, we need to know what is this, and we can design and we can do something to avoid this effect, to increase the reliability of our device. And the third part we call the thermal migration. Based on this term, you know, this atomic migration is due to the thermal driving force. Thermal driving force means we will apply the temperature gradient on this material, and this gradient will drive the atomic movement. Okay, in the fourth part, we are going to talk about the capillarity effect. What's the capillarity effect? Actually, is when you have materials with curvature, it is a curved materials, and the atoms at the surface has a higher definitely have because the atom the curvature is different, right? So the potential chemical potential or surface potential will vary with the curvature. Under these conditions, the atoms at there's definitely a surface potential difference happen on the surface of these curved materials. So the surface potential gradient or chemical potential gradient will serve a driving force to drive this atomic movement to reach the surface planization. And the last part we are going to talk about is the stress migration. As we mentioned before, in the capillarity effect part, the atoms be moved or be pushed from the convex region toward to concave region due to the atoms has a higher surface potential at convex region, so it will going to move to the concave region with a lower surface potential to decrease the total free energy of the system. And the last part is stress migration. As we know, there's lots of defect inside our materials. So if there's a age dislocation happen in your materials, and you can identify the region with age dislocation belongs to compressive region, and atoms located inside this region will have a higher potential energy. So this atoms is going to be pushed or moved toward to tensile region to decrease the total free energy. So this is we call a stress migration. And some people call this kind of migration, it belongs to long distance transport. Okay. So last part we are going to teach you how to deal with the system be applied on like 2 or more driving force in the meantime. How can we deal with this kind of cases? So the driving force, you need to summarize all the potential terms and take the gradient minus gradient terms on it. Then this will be serve the total driving force to drive this atomic movement. So we will talk about this later at the end of this lecture. Okay, so let's move to the first part, diffusion. In the first section, we are going to talk about the diffusion in solid materials. And first of all, we are going to tell you the relationship between the diffusivity and mobility. Diffusivity, as you know, actually is the parameter to describe how fast the atoms moves inside our materials. And mobility actually, what's the definition for mobility? When you when you apply a unit driving force, what's the velocity of these moving atoms? We call it mobility, right? So in your mind, probably you will think about the relationship between the diffusion and mobility will be something like a proportional. Okay? But we need to demonstrate or derive the real relationship between these two material properties. And the second part, we are going to introduce you actually based on the different material systems and different observation coordinates in our systems. We have 3 different kinds of diffusivity. The first one we call it is a self-diffusivity, and the second one is intrinsic diffusivity, and the last one is interdifusivity. The difference between these 3 different diffusivities based on different material systems and also the different observation coordinate, or you call the different reference coordinate. And the last part in these sections, we are going to talk about what is the Kirkendall effect. And the characteristic for this Kirkendall effects are the void formation and the lattice plane shift. And also, what's the applications for this Kirkendall effect in material synthesis? So let's move to the first one. In order to well describe the mass transport in solid materials, so I believe you know the flux, right? This is mass flux, and the unit for mass flux is how many atoms passing through a specific area in certain time period. We call this as a mass flux. Mass flux can equals to concentration times the velocity. Concentration actually is how many atoms in the unit of volume, and also the velocity is actually what's the distance what's the total distance of this atoms moving within this time period. So it's a velocity of this diffusing atoms. So flux J equals to CV, and velocity actually equals to what? As you know, mobility equals to velocity divided by force, right? Mobility is defined by when you apply a unit driving force. What's the velocity of this moving atoms? So V equals to mobility times driving force. So we substitute this velocity with the mobility times the driving force. So here we can express the flux equals to mobility concentration times the driving force. Okay? And the driving force part, some people were curious about what's the driving force. That was depending on the boundary condition or the condition we're talking about in your material systems. So can be the electrical field. So you can use the voltage divided by the distance. Okay? So let's move to this slide is going to derive what's the relationship between the mobility and diffusivity, and also that's a very famous relationship we call the Einstein relationship. Okay, so we are going to derive that. In order to show what's the relationship between mobility and diffusivity, in the beginning, I believe you will write these two equations together, right? And next, don't forget, in order to take this driving force here actually is a minus chemical potential gradient. So in order to deal with this chemical potential gradient change, so you need to have a quick review for what's the chemical potential. Chemical potential of atom A actually is when you added one more of atom A. What's the change in Gibbs field energy? We call the chemical potential of atom A, and it is dependent with its composition XA. Based on this, you can write down like mu A equals to partial G partial NA, and this is the result. Actually, I just copied this result, right? And here, there's a very important part here. XA is the atomic fraction of atom A. So I'm going to substitute concentration times average times omega, which means the average atomic volume, to substitute the atomic fraction. The reason for this is I try to link these two equations. So I try to substitute this into as a function of concentration. So the idea would be go this way, so I can successfully to convert the chemical potential or link the chemical potential with a concentration related term, right? So this is ideal. Okay, so some people probably concern XA atomic fraction can equals to CA concentration of atom A times the average atomic volume. Really? So let's check the unit here. So what's the constant? Okay, so the average atomic volume will around this range. Okay, and what's the unit for concentration of atom A will be the numbers of atom A per unit volume, right? If you times the average atomic volume, so the upper portion will be the what? Will be the total volume of atom A divided by the total volume of these materials. So you will get you can have an approximation with the atomic fraction XA. So based on this, you know XA equals to XA CA times the omega, right? So let's take the gradient on this equation. Gradient means you partial with the distance, right? So if I partial with the distance, mu A0 actually means what's the chemical potential of atom A in pure material. So this is not going to, when it's partial with distance, this chemical potential of atom A is not going to change with the distance, right? So you got the 0. And this term you can divide it into log Ca plus log omega. Kt log Ca, when you partial with the distance x, then you can partial with x with log Ca. You partial with the x, you got the 1 divided by Ca and Ca gradient. And the last term here, Kt log omega. Omega definitely a constant, right? Divided of partial with the distance will becomes to 0. So you got this relationship. What's the relationship? Is between the chemical potential gradient with the concentration gradient. So based on this relationship, we know that actually chemical potential gradient is proportion to the concentration gradient divided by Ca times the Kt, right? So it's reasonable why some people were misunderstanding that the concentration gradient is a driving force for diffusion phenomenon. Okay, so let's move forward here. We know there's a relationship between the chemical potential and concentration gradient. So let's substitute this term with this term here. So I will get a mobility concentration driving force and substitute this term with this term. And see, we can delete that. The rest of part will be mobility times mobility, right? And Kt and concentration gradient, Kt concentration gradient. And this flux actually is the same with this one. So compared with these two equations, we know the diffusivity equals to mobility times K, Boltzmann constant times absolute temperature. So now we get a very famous relationship between the mobility and diffusivity. Is mobility equals to diffusivity divided by Kt. So in this slide, there are three very important information you need to learn. The first one is X atomic fraction is equals to concentration times the average atomic volume. You are going to use this always or usually in the following slides. So please remember this relationship. And second one is the relationship between the chemical potential gradient and concentration gradient. And the third one is the mobility, the relationship between the mobility and diffusivity. Also, okay, so please highlight these 1, 2, 3 informations. Okay, so we finish this part, then we will move to describe the 3 different kinds or types of diffusivity. So as you know, diffusivity actually is intrinsic material properties to describe how fast the diffusing atoms moves inside our materials. So based on different material systems and also the observation reference coordinate, then we can simply divide the diffusivity into 3 different types of diffusivity. And before we move forward, so I have a question to you. In the course entitled Material Science and Engineering part, I believe you guys already did learn about the diffusion, right? You always calculate how much time you need to dope the carbon atoms inside the steel, right? You calculate lots of diffusion stuff, right? And the information provided by the questions only give you the diffusivity equals to certain value, right? They didn't address what kind of diffusivity is that. It's a little bit weird, right? If I say there's three different types or kinds of diffusivity, why in previous course actually they didn't mention too much about identify what kind of diffusivity he mentioned in that questions. The reason we will explain after this slides. So this is also the reason why we want to introduce you. Actually, there are three different types of diffusivity. Okay. So the first one actually is we call the self-diffusivity. Use the symbol D star. In this case, it means the diffusivity of component I in a chemically homogeneous medium. So it means the diffusivity of component I in a chemically homogeneous medium. The question here would be, what's the chemically homogeneous medium? Some people probably will answer, does that mean the pure materials? Yes. Actually, is the less uniform concentration, no concentration variation in your materials. In this case, we call it a chemically homogeneous medium. So it can be a pure metal or the alloy. Highlight the alloy, for example, like if I have an alloy like this, and 0.3A and 0.7B, and when I'm if you consider the atom A, actually the concentration is uniform inside this material. If you consider the material B, actually is uniform inside these materials. So in this case, self-diffusivity, these are actually these materials can be a pure metal or the alloy, like this. So some people probably were curious about. So in this case, actually, the concentration, there's a uniform concentration, no concentration variation. So what's the driving force for this self-diffusivity? Actually, the only driving force exists in these materials is the thermal energy. So this thermal energy will allow these atoms to have a randomly walk. So what's a randomly walk? Is the average displacement of the atoms equals to 0, right? So the atoms can freely jump right-hand side or left-handed side and just move around. But totally, if you observation for a very long time of period, the average displacement equals to 0. Okay, this is diffusivity actually. Is we call a self-diffusivity, D star. And we still have two diffusivities. The first one we call intrinsic diffusivity, D, and the third one is interdifusivity, D. I use this as with a head. So what are the diffusivity? The first one is the diffusivity is a composition dependent. Means the diffusivity will change with the composition of the materials. And the difference will be the material we are talking about is a chemically inhomogeneous medium. Inhomogeneous medium tell you that the material system we talk about will be like this. For example, like this. When you bind A material with B materials, then we have a diffusion couple like this. And in this case, the concentration is not uniform, right? Have a concentration variation. If you talk about the concentration profile of atom A, it will be like this. If you want to draw the concentration of atom B, it will be like this. So that's a concentration variation happen in your material. So it's a chemically inhomogeneous medium. Okay, both these are composition-dependent diffusivity and also in the chemically inhomogeneous medium. So what's the difference between these two diffusivity? Would be the observation coordinate, which means this intrinsic diffusivity actually you stand inside the materials. So the observator stand inside the materials. So we call this is the crystal coordinate. But if you stand outside the materials, for example, like you stand in your lab and you watch the material on the desk, and in this case, we call this kairos coordinate or reference coordinate or observation coordinate is a lab coordinate. Okay, so I will explain why this these two diffusivity will difference varied with the reference or observation coordinate. Let's take this AB diffusion couple as an example. If you try to heat these materials up and allow the interdiffusion happens in between, then we assume the flux JA is larger than JB, which means less more A move to the right-handed side compared and less B move to the left-handed side, right? Okay, in order to reach the net flux equals to 0 at any specific plane, so this one is larger than this one, right? So there's definitely a vacancy flux toward to left-handed side to allow JA equals to JV plus JB. And this is the first thing you need to know. And the second thing you need to know is regarding to the interface. This is quite important because JA is larger than JB. There's more A move to the right-handed side. This agency A is going to push this interface toward to left-handed side. So that tells you the plane, the interface is going to moving inside these materials. So this moving interface movement causes the difference in intrinsic diffusivity and interdiffusivity. So if you stand inside or on this interface, then the diffusivity you measure or observe belongs to intrinsic diffusivity. Because you stand on this interface, so you are going to measure how many atoms passing through this interface, right? Which we call the diffusivity. Would be different if you stand outside, which is we call lab coordinate, and measure how many atoms passing through this interface. In this case, we call it interdiffusivity. So let's use the cartoon to explain the difference between the intrinsic diffusivity and interdiffusivity. And don't forget the symbol for intrinsic is just use a D, and the interdiffusivity you give it a hat here. Okay, so now we also have an AB diffusion couple. In this case, when diffusion happens, interdiffusion happens, which means like probably you heat these materials up. Then you in this case we assume JB is larger than JA. So as we mentioned, the interface is going to move toward to right-handed side, right? Because more B move to left-handed side, it's going to push this interface toward to left. Oh, sorry. There's more B move to the left-handed side, and this B is going to push this interface toward to right-handed side. So when you stand outside or in the lab, then you can observe the atoms, the interface move, right? And in this case, the diffusivity you measure is we call the interdiffusivity. But the intrinsic diffusivity actually is when you stand inside these materials. So the diffusivity you measure will be we call the intrinsic diffusivity. In this case, probably maybe you will have one questions. So in most of cases, what kind of diffusivity we measured in our lab usually is interdifusivity. Okay? Okay? And by the way, based on this, you know that the vacancy, in order to reach the net flux, total net flux at any specific plane will be equals to 0. So you know there's a vacancy flux toward the right-hand side. Okay, so why we need to mention this vacancy flux? Because when interdiffusion happens, you can observe some vacancy be created. This is the reason, and this is highly related with the Kirkendall effect we are going to introduce to you in the following slides. So we will talk about that later. Okay, so next we are going to spend like 3 or more slides to demonstrate what's the self-diffusivity, intrinsic diffusivity, and interdifusivity. What are the relationship between this diffusivity and the direct and coupling coefficient, this intrinsic material property, and also what's the relationship between the concentration part? Because you know it's a concentration dependence diffusivity, right? So let's move to the first one, self-diffusivity. When we talk about self-diffusivity, actually we talk about the material system definitely is either belongs to pure materials or the alloy like this. So let's take a look on some definition. Component I and its radioisotope I star have the same chemical potential. So what this means actually is the question would be how to measure the self-diffusivity. Because we are going to explain the relationship between this diffusivity and the direct and coupling coefficient and concentration part. So we are going to the question will be how to measure the self-diffusivity because the concentration there's no concentration variation. So how to measure the self-diffusivity? So the way here is like you can use a radioisotope to implant into this or to substitute some component I, and we can plot or monitor the diffusion profile of this radioisotope I star. Then we can calculate or estimate the self-diffusivity. So why we use the radioisotope I star? Because they have same chemical properties. So you can consider that we still the concentration, the total concentration along these materials still maintain the constant because we just substitute some I with I star. Then we can measure the profile of I star, right? So in this case, what are the driving force? Although there's no spatial variation in chemical concentration, but I and I star actually they are different, right, in chemical potential. So there's a spatial variation in chemical potential. So this was serving a driving force to drive this mixture between the I and I star. So in this way, we can the driving force. This process will increase the entropy, right? And this process, as we mentioned, there's a chemical potential difference between I and I star. Then that will drive this mixture and lead to the increase of entropy. Okay, so now you know how to. So probably you have some idea, right? If you don't end the radioisotope I star, then we cannot measure the self-diffusivity. But as long as we use the radioisotope I star, then actually we provide the driving force, right? So So the D star which we measure actually is not exactly the same with the same is the real diffusivity of component I, but it's near. Can have a this like is very is have a this kind of approximation is similar with diffusivity of component I, self-diffusivity of component I. Okay, so in this case, self-diffusivity D star equals to KT times the direct coefficient L11 divided by concentration of component I minus the coupling coefficient divided by the concentration of radioisotope. So this is the self-diffusivity with proportion to the absolute temperature and related to the direct and coupling coefficient and also the concentration of component I and radioisotope. So some people probably were curious about how we can get this relationship, how we derive this relationship between the self-diffusivity and corresponding parameters. So the details are shown in the lecture note on page 14. So probably you can, I just copy and highlight we just I just copy and copy one slide, and you can get this information from lecture note on page 14. So in order to, I will demonstrate how to derive the self-diffusivity to here. This is the same with this one, right? Okay. So the idea here is we start from formulate the flux of component I and the flux of radioisotope component I. Okay, radioisotope I, and as you know, based on the force flux relationship, the direct driven by F1 and couple and indirect driven by F star 1, and also regarding to a radioisotope, the direct driven by F star 1 and indirect driven by F1 and times the coupling coefficient. Okay, so I believe you can write down the flux for component I and radioisotope I. And before we move to details, I want to show you some idea. In order to get the D star, so definitely after series deviation, you will formulate like a J, the flux of radioisotope I equals to minus D star concentration gradient. So as long as I can substitute this term in also the partial concentration star 1 partial with respect to x, then the rest of part belongs to D star, right? So this is the whole idea of these deviations. Okay, so next we are going to show you how to substitute this term into this concentration of radioisotope I respect with x. Okay, so now you know this relationship, right? So now we try to formulate the driving force part. So my question here would be, do you know the driving force? What's the driving force in this case? Probably some people will answer the chemical potential gradient. But my question would be the chemical potential gradient with respect to who? We have component I, right? And also we have a radioisotope I. And also don't forget, definitely there's probably a vacancy inside the system, right? So the the chemical potential gradient would be respect how to formulate the chemical potential gradient will be the question to be answered. So in this case, in order to answer these questions, I will introduce you a very famous constraint we call a network constraint. This constraint be applied when following conditions. When there's some changes in one component, if the changes in one component will lead to the changes in other components in your system. In this case, you can use this network constraint. So in this case, we know when you summation all the components and the Ni will be equals to 0, right? Because probably this component will you lose 5, then this 5 will move to the other component. So you have -5 and +5 will equals to 0. So this can be what? Can be an example like if you have a, let me give the other examples here. If we have a chemical reaction, for example, like we have A2 plus B2, and this reaction will have 2AB, right? So this is another example you can use network constraint. So the A2 plus dB2 plus dAB must equals to 0. So this is a network constraint. Okay? And for mature scientists, actually, you can consider you have atom and vacancy inside your materials. So the atom and the vacancy plus the vacancy equals to 0, the same idea. Okay, so next I'm going to show you how to get the driving force term for this under these cases. So first of all, you use the first law and second law of thermodynamics and ended the composition change term here we derived in lecture 1. Next, I'm going to substitute this term with these two terms. What I did actually, I just depart this term from I equals to 1 to NC minus 1, and I ended the last term here is when I equals to NC, so it will be mu NC dC NC. Just depart into these two terms. Then next, I try to substitute this term. So what's this term? Actually, based on this network constraint, we can express like this. Also the same, right? Summation I equals to 1 to summation to NC minus 1 dNi minus this 1 equals to dNc, right? If you don't know why, you can just move this term to the left-handed side. Then you will find that this term plus this term equals to 0. The same idea. Okay, so that's times the mu NC together. Because mu NC times mu NC, you are close, right? Mu N minus mu NC dNc. So we use, actually, I times the minus mu NC, right? Minus mu NC. So the left-handed side will minus mu NC dNc. It's very close. And the right-handed side is plus mu NC summation I from 1 to NC minus 1 dNi. Okay? Okay, so next, these two terms are similar, right? The only difference is dC, NC, and dNc. So this is a numberless concentration. So I divided this term by volume. So this term will be the CNC, right? And this will become the DCI, right? So this is because so this term the same, right? and this term after divided by volume, this term will be equals to this term, so use this term to substitute here. So because divided by volume, so it will be the Ci, and we take the dCi out here and put the chemical potential term inside. So based on this, compared to this term, we know the driving force for moving the component I will becomes to this, will be the chemical potential I, component I minus the mu Nc will be relative to component Nc. The Nc here, please mark it. It can be considered vacancy. So the driving force here will be the chemical potential of atom I minus the mu vacancy, take the minus gradient on it. So let's move to, so based on this idea, please go back to the lecture note. The driving force here, if we the driving force for component I actually is mu I minus mu V, and for the radioisotope I is also minus to mu V, because we allow or assume the Nc component equals to vacancy. So we can substitute the chemical driving force term with these terms. And that's a very important assumption here. Net flux equals to 0, so the J1, the flux of atom component 1 and plus the flux of radioisotope 1 plus the vacancy will be equals to 0. And as you know, when the concentration of component 1 and plus the concentration of radioisotope 1 plus the concentration of vacancy equals to constant, because the total concentration of all components should fix, right? Under these conditions, we take the gradient term on this equation. Gradient term, you can directly delete this term, and also, right? And also, we assume, probably we talk this later. So that's a very important assumption after here. So we assume all the vacancy are under thermodynamics equilibrium. So it means the mu V, we assume mu V equals to 0. Means the chemical potential vacancy equals to 0. We assume that. So we can delete this mu V term. And use the Einstein relationship. Chemical potential gradient equals to kT divided by concentration times the concentration gradient. And this mu V equals to 0, so we can get this relationship. This relationship is very important because it will help us to substitute this term by these terms by concentration part. Okay, so next I'm going to focus back to the J1 part. I just use this Einstein relationship to substitute the chemical potential gradient term and becomes to here, right? And the question now will be here, the following. The purpose, as we mentioned, we assume under the thermodynamic equilibrium condition, mu V equals to 0. Because mu V equals to 0, so we can expect JV equals to 0. Because that's uniform, the chemical potential are the same, right? So let's know JV. So J1 equals to J star 1 equals to minus J1. So we can reach here. So as long as I substitute the J1 with this partial concentration star 1 gradient with the concentration star 1, then I can know the D star, right? So how to do that? So J1 expressed like this, right? So we substitute this term here, so we got this, right? So the next part is how to substitute. So we directly put this J1 here, so you got minus, I just copy here, right? And next I'm going to change the concentration gradient part with this part. And how to do that? So you just take the gradient on this term, So you got a relationship actually partial c partial x can be expressed minus partial c star 1 partial respect with x. So you substitute with this term minus this term. So the rest of part actually is a self-divisivity d star. So we know the self-divisivity d star can be expressed like this. So this is a whole. This is a details. These details tell us how to derive the self-divisivity.